stomach, it acts as a food blender. It actually grinds the food very slowly. It's a reservoir where gastric juices can digest the food. It's very distensible. In other words, you can stretch it out. You can hold 2 to 3 liters of food. Contrast that to a newborn stomach, which only holds about 30 mLs of milk. It's the primary place for chemical digestion because of all the acids and enzymes. With a pH, you can get to like an acidic brew of about 1. It's very acidic. So, stomach. Functionally, it's food blender, a grinder. The product of stomach digestion is acidic chyme. Now, the anatomy of the stomach, if you were to remove it from the cavity, it is intraperitoneal. You can see that the space behind the stomach is occupied by the pancreas. If you look at the middle picture, to remove the stomach, you'd have to cut along the greater curvature and the lesser curvature, and cut on this end where the duodenum is, and this end where the esophagus is. You can look at it in isolation and study the regions of the stomach shown here. The regions include the fundus of the stomach, which is basically the superior round part. Okay. The cardia of stomach, well, it's called that because it's right next to the heart. Right above that, you have the diaphragm, and right on top of that is the apex of the heart. I'll just say the heart lies on top of this region. Now, the large portion of the stomach is the body. Body of stomach, largest portion. And then you can see the body, it funnels into the pylorus. The pylorus of the stomach, this region, it has, well, the word means gatekeeper. As a gatekeeper function. Inside it, you'll see the pyloric sphincter. That performs this gatekeeper function. It's guarding the duodenum from receiving too much acidic chyme. Guards duodenum. From receiving too much chyme. The other thing to notice is the coloration in this picture. It's actually pretty accurate to what you see in a cadaver once you open up the body cavity. Also note the curvatures, the greater and lesser curvatures, named for, the greater and lesser omentum that kind of attach to them. So I'll just list them. Greater, lesser curvatures of stomach. Mesenteries attach here. Again, those are the greater and lesser omentum, which we talked about yesterday. I'm going to move on. If you dissect away the serosa or adventitia, you can see the muscularis externa. So in this picture, notice how they left a little bit of serosa on top there. but then they cut it away everywhere else. And this is an illustration of not only the inside of the stomach, but the 3 layers of muscularis externa, which is unusual. Normally it's bilayered, but here it's trilayered. So in the stomach, you have 3 layers of muscularis externa. Trilayered muscularis externa. So again, those 3 layers, going from inner to outer. The innermost layer is an oblique layer. Oblique layer of muscularis externa. Be sure to write it all out, okay, if you're identifying it. And then the layer external to that is a circular layer. Of muscularis externa. And the outermost layer is longitudinal. The fibers run longitudinally. Longitudinal layer of muscularis externa. So I'll point them out real quick. The innermost layer, the fibers run obliquely to the other 2. Oblique, circular, longitudinal, in that order. The pyloric sphincter is also shown here. You cut this open. It's that sphincter right there. You can even see inside that the internal appearance of the mucosa is like, well, it's not smooth, it's wrinkled. Those wrinkles shown here are called rugae. So note the rugae, the wrinkled appearance on the inside of an empty stomach. Rugae. These longitudinal wrinkles. Remember, the stomach can distend, it can stretch, so those wrinkles will stretch out. Hold 2 or 3 liters of food. That's a lot of food. Next time you get a plate full of food at hometown buffet, just look at it. All that's going right here. Okay, about 15 minutes. Your stomach's got to hold it all. Digestion. Okay. Then you go back for seconds. Another whole plate of food. Okay, that's a lot of food. Anyways, there's the serosa. And your 3 layers of muscularis externa. That's the innermost layer, oblique, circular, and it's hard to see, but there are lines running this way. That's longitudinal. Those are the rugae. Okay, you can barely see the pyloric sphincter up there. That's not a very good picture. Let's move on from this picture. This one's in the room. All right, so this is illustrating the grinding and propulsion of food in the stomach after you've eaten a meal. Let's see, this is kind of physiology here. So there's about 3 peristaltic waves per minute that occur in the stomach. 3 peristaltic waves per minute. And with each wave, what you see is a phase of propulsion. In the middle, they call it grinding. Remember, the stomach is a blender. And then the last phase, they call it retropulsion. Retropulsion. Well, anyways, what you're doing there is look at the pyloric sphincter. It's closed in the first and third phase. First phase, you're just pushing the food forward toward the sphincter. It's closed there. But in the grinding phase, it opens slightly to allow just a few mils into the duodenum. And then retropulsion, it kind of like backwashes a little bit. But in both phases, first and third, it's closed. It only opens a bit during grinding. Sphincter opens slightly. And that's when you allow I'll say 3 ml of chyme to pass. Like you're just slowly letting the food forward because, well, the intestine can't accommodate as much food as the stomach can. So when you feel full and you're waiting for your food to go down, that's literal. Okay, it's going down a few mils at a time. You got a couple of liters of food in there. Now, all that gastric secretion, we got to talk about that. The stomach is highly regulated by different mechanisms in different phases. Eating will trigger different phases of gastric secretion. We call it head, stomach, small intestine, just to name the phases. Phases of gastric juice secretion. This creates the chyme of the mixture of food and acid and brew. Well, you know, if you ever vomit, it's vomit. And but that is the product of the stomach mucosa. And the process starts, well, the juices start all in your head. Okay? Just to get the juices flowing. This is before you start eating. You're just, I'm hungry, you know, and you drive to the restaurant, you can smell the food, and it increases your appetite. You see the food, you smell the food, you're watching what other people are eating inside the restaurant. It gets you hungry, and the process starts before food has been introduced to the stomach. Then when you sit down and get your food, that's the main phase. Maybe an hour or two, the gastric phase, and maybe a few hours later, after you're done, there's the intestinal phase to finish off the gastric secretion. And so we'll talk about the details of each phase. Here they show the cephalic phase, which is basically all in your head because gastric juice production begins before food is even introduced to the stomach. Secretion of gastric juice begins before food arrives. And just to define what I mean by gastric juice in this lecture, I want you to think of the cells of the gastric gland that secrete these things. Gastric gland cells. And those include mucus cells. Well, they secrete mucus. Then they list chief cells and then parietal cells. Chief cells will secrete something called pepsinogen that helps digest proteins. And then the acid-secreting cells are the parietal cells. They'll secrete a combination of HCl as well as intrinsic factor. An alternate name for chief cell is peptic cell because they secrete pepsin. So have you ever seen the term peptic cell in your studies? Chief cell is what we're calling it here. Well, anyways, the mucus, the pepsinogen, the HCl, that's the gastric juice. And as you can see here, just the mere sight, thought, aroma gets it going before food even begins. And you start to order food, and if you order appetizers, the idea is a little bit of food will increase this process before the main course arrives, correct? Well, the next phase is the gastric phase. This is the phase when you're just kind of like getting the food in your mouth, you know, over a course of an hour of eating dinner. Sitting down to eat, finishing your meal, most of the gastric juice is produced. So they show a full stomach here. Called the gastric phase. say this is 3 hours long. So you eat for about an hour, and it's happening a couple hours later, and it produces most of the gastric juice, about 2/3 of it. Anyways, what I want you to understand is most of the physiology. There's two things going on here. For the gastric phase, there's a neural trigger and a hormonal trigger, those two things. The neural trigger, what's the trigger? Well, as food arrives, it stretches the stomach wall. They call that distension on this slide. Lots of food, a full stomach. But also, if you eat protein, proteins tend to elevate pH. So the combination of distension, elevated pH, those are neural triggers. Increased pH. With increased pH, there are chemoreceptors that can trigger a reflex. And for the distension, there are stretch receptors. Both of those, the reflex, so it has to do with the vagus nerve. Anyways, think of the neurotransmitter ACH. There are cells in the gastric gland, the ones we just listed, that have ACH receptors. And so they show you that these here trigger gastric gland cells to secrete the gastric juice. I don't want to relist them, I'll just say gastric gland cells. So the ACH stimulates gastric gland cells. So that'll get you some of the juice. The other trigger is a hormonal trigger. If food advances to the pyloric region and there are partially digested proteins there, in this region only, the gastric cells have these enteroendocrine cells that will secrete the hormone gastrin, which will trigger chief cells and parietal cells to secrete more of their juices. So, hormonal trigger. If partially digested proteins, PROS, you're chewing your steak too fast, slow down, chew slower. But if it's not getting fully digested, if partially digested proteins advance to the pyloric region, in this region only, gastric glands have enteroendocrine cells. Gastric glands here have enteroendocrine cells. Sometimes I just call them G cells for short, because they secrete gastrin. Okay, well, gastrin is the hormonal trigger, so I'll underline it with the red line. And you can see that the figure, it's the gastrin which will target, I'll draw an arrow from gastrin to gastric gland cells. It'll also trigger it. So you have two triggers here. The hormone is gastrin, the neural trigger is ACH. So this gets you most of your gastric juices from the gastric glands. And let's finally look at the gastric gland. They're contained within the mucosa of the stomach wall. Here they show you one in the pyloric region, so they're going to show you the G cells. gastric gland structure in the mucosa. So look at the figure. We're looking at the top, just the mucosal layer. You see how it's all folded in, where the surface epithelium looks pitted. Now, if you take a close look, those pits actually lead to a couple few gastric glands down here. Don't confuse the glands down there with the top. That's the pit. Gastric pit on top leads into gastric glands below. So that's the structure there. If you take a closer look at just the mucosa there, you got pit, neck, gland from top to bottom. I don't really teach the neck. Just know that the pit leads to a couple few gastric glands down there. And deep inside the gland, you have all those cells that we've been talking about. Well, the three we've been talking about are mucus parietal chief. But if you're in the pyloric region, you have these green enteroendocrine cells also. It's the fourth one. So this is just looking at deep in the gastric gland. And, well, the most numerous cell is the purple cell. It's the chief cell. That's what they're called. And they secrete the pepsinogen. Notice that the pepsinogen is the inactive form, but with low pH, it'll activate it to its active form. And this is an illustration of a very important concept in digestion. You don't want to auto-digest the digestive tract. So you secrete things in an inactive form, and they, by design, do not activate until they reach the lumen. In this case, the trigger is low pH. So, pepsinogen is released when you have protein, so this is inactive. Okay. And usually, like, if you're not eating between meals, stomach at rest, maybe the pH in the stomach is something like 4 to 6. But if it's active, you're eating, and the pH becomes less than 3, that's low enough to activate pepsinogen and convert it to its active form, pepsin. Pepsin will, hydrolyze, it'll break the peptide bonds, right? Pepsin, peptide bonds, digest proteins. That's the connection there. And then you see the other two cells, those fuzzy-looking sideways pitchforks. They're designed that way to increase the surface area for acid secretion. So here's a picture of a triangular pitchfork-shaped parietal cell. Not to be confused with the chief cells that secrete pepsinogen. They secrete the chloride ion and the hydrogen or proton separately, and it forms HCl in the lumen. That's what they're illustrating to you there. And then the HCl will lower the pH. Okay. And in exchange, well, they call these HK pumps. Those are those proton targets of those drugs, omeprazole, the proton pump inhibitors, which help patients suffering from heartburn or acid reflux. These are the cells you inhibit. Well, anyways, this alkaline tide, that bicarbonate is very important. It'll help neutralize some of the stomach acid to protect the lining of the stomach. So, anyways, for this, this is the parietal cell. Remember, the pepsinogen is secreted by the chief cell. So don't confuse that. So what happens is those mucus cells, when they secrete the mucus will trap the bicarb, creating this physical and chemical barrier. So at the level of the cell, it's pH 7 neutral. So that way you don't auto-digest the stomach lining. Of course, you can still get stomach ulcers, but everything's working okay. You should know. So, mucus traps bicarbonate, slippery, creating a physical / chemical protective barrier. Prevent ulcer. All right, so I'm going to move on to the third phase of gastric juice secretion. They call it the intestinal phase because, well, food has kind of moved on down to the intestine, and the intestine is actually just trying to slow or inhibit stomach churning and gastric gland secretion. So it kind of like, it's kind of pacing the stomach to slow down so it can process the food that's being passed to it. It's largely regulated by all these hormones that I have listed here that I want you to know. So when food makes it past the pyloric sphincter, you have the arrival of chyme to the intestine, or duodenum. Arrival of chyme to duodenum. So this is these are all duodenal intestinal hormones that are at work here to help the intestinal phase. The primary goal is to inhibit the stomach, just to pace it, okay? So you don't receive too much chyme at once. Inhibit stomach activity. The intestines are like the brakes. They slow down. I can't hold as much as you. Okay, stop eating and just let the food go down slowly. That's kind of what we're doing here. Now the hormones that help the digestion are listed there, but it depends, the trigger for their release depends on what's in the chyme. And I list the triggers in the PowerPoint slide. For example, if there's fat, protein in the chyme that's arriving, that's the trigger for the release of cholecystokinin. Now, I just usually abbreviate that CCK. But it's a word that means move bile. Chola means bile. Kinin means move. Cysto probably refers to the gallbladder. But anyways, what this does is it stimulates gallbladder contraction. Gall bladder contraction. The gallbladder stores and concentrates the bile that the liver produces. And by stimulating its contraction, you're going to squeeze it into the duodenum. But what you got to do on the other end, you got to loosen the valve. Okay, you got to open the valve on this end. That valve is called the hepatopancreatic sphincter. It's a sphincter that you have to relax. So CCK relaxes the hepatopancreatic sphincter. So when you squeeze it, the bile washes into the, it's squeezed into the duodenum. Relax. Hepatopancreatic sphincter. The third thing it does, it will stimulate the release of pancreatic enzymes from the pancreas. So it stimulates release of pancreatic enzymes. So that's a very important one, CCK. The other important one is not listed second, it's listed third, it's secretin. So let me present that next since it's the second most important. Just the arrival of chyme itself will stimulate its release. Secretin, it's the major one. I mean, it's called secretin. It's going to make liver and pancreas secrete stuff, basically. It's going to stimulate the bile production from the liver. Bile production from liver. And it's going to stimulate this bicarb-rich juice to be released from the pancreas. Pancreatic bicarb-rich juice. Okay, so it's bicarb. It's not the enzymes. Enzymes are for digesting food stuff. But bicarbonate, that'll neutralize the stomach acid. So that's the main. These are the main two: CCK and secretin. But I'll get mentioned to the other ones. So I skipped GIP, gastric inhibitory peptide. If you have fat and or carb, CHO, maybe glucose, that'll stimulate the release of, I'll just give it by its abbreviation, gastric inhibitory peptide. By its name, it actually does inhibit stomach churning. I'll say inhibit stomach activity. But it's not in the name, you can't tell, but it's going to also stimulate the release of insulin from the beta cells in the pancreas. Insulin release. Yeah?
Stomach churning, isn't that like some type of, like a disease? Or?
No, that's the normal performance of the stomach, so it can act like a blender to mix food up.
Yeah, I looked it up online and it said it was like a virus in the stomach.
You have to show it to me later. Stomach churning or motility is a normal function of the stomach. I'm sure there are diseases that cause abnormal things, but yeah, it is normal. All right, two more, VIP and gastrin. Now, VIP is stimulated, again, just by chyme. It's called vasoactive intestinal peptide. I'll just abbreviate it VIP here. It'll dilate intestinal capillaries so that you can increase the absorption by increasing the blood flow there. So, dilate intestinal capillaries. That'll help increase absorption. That's the food coma hormone, right? Because that makes you sleepy. All the blood rushes to your stomach for and intestines for digestion. Okay, then there's gastrin itself. Again, there's gastrin. So gastrin, if there's undigested proteins, that'll stimulate the release of more gastrin. I say more gastrin because it primarily comes from the stomach mucosa, but it comes from the intestine too if the undigested proteins reach that far. That's the only one where the gastrin will increase stomach activity. All the other ones, in addition to all these notes, they actually all inhibit stomach activity. Okay? This is the only one that's an exception. It will increase stomach activity. So I'll try to draw a line just to kind of symbolize that. Well, like I say at the top, they all inhibit activity, but this one increases it if food is still undigested as it reaches here. So as food moves on to the duodenum, we're done with the stomach now. The duodenum, in terms of anatomy, if you look at this picture, it's not much to look at. It's just the first 10 centimeters of the small intestine. Now the stomach was removed from this picture. Cut there, and you cut there to remove the stomach. There's no liver, and they cut the other end of the small intestine. So this first 10 inches, that's the duodenum. It starts intraperitoneal, then goes retro. So this is all retroperitoneal. You do not have to know these 4 parts, D1, T2, D3, D4, but be aware that D2 has this structure here. That structure is where the liver and pancreas will secrete their juices into the duodenum to mix with food to help digestion. So let me clear this. So it goes retro, peritoneal, and that second part, that descending part, you're going to want to look for this structure called a major duodenal papilla. Now on the slide I say hepatopancreatic ampulla, but that term I don't see used in your atlas, so I'm going to use the term that's in your atlas. The major duodenal papilla. And on some, I think on your study guide, I may not even have the word major, I just may call it duodenal papilla. But know that as the point at which it's going to receive the liver and pancreas secretions there. I have some more pictures looking at the duodenum. The picture on the left, you can kind of see how it goes retro and pops back intra. That's kind of more like the picture we were just looking at. It's mostly retroperitoneal. Here they cut off the duodenum. The next part of the small intestine is jejunum. You can see how jejunum would follow the mesentery. At some point it becomes ileum. That's the end of the ileum, the end of the small intestine. Here's the beginning of the large intestine. Here's a picture that we looked at just now. Here is the duodenum isolating. So if you back it up all the way to the stomach narrows to the duodenum, and inside here there's that big sphincter, that pyloric sphincter. Pyloric sphincter. And then there's these longitudinal folds that run this way and that way, lengthwise with the stomach, and those are the rugae. But then you go to the duodenum, and the duodenum has these circular folds. Okay, they kind of show it in the picture on the right. And those are called plica. Plica circularis. These circular folds, and there's a functional reason for that. In the stomach, you have these longitudinal folds, and the sphincters, it kind of allows the chyme to slosh back and forth as it gets grinded. But when you squirt just a little bit to the small intestine, it spirals around the circular folds. That increases the contact time. There's also a lot of segmentation in the intestine that helps the mixing. But those circular grooves help, they help for the absorption, so the food stuff doesn't just wash right by with no time to absorb. Now that little major duodenal papilla is right there. You'll be expected to identify that little spot. So on my picture, it's something like a little bit here. A little nipple-shaped bump. And it's receiving secretions from the liver to the bile duct, the bile. I'm going to draw a green duct going up here. But also the main pancreatic duct shares that space. Main pancreatic duct. Remember, liver and pancreas, those are your major organs, major accessory organs of digestion. They're not a part of the GI tract, but they secrete into it. Another important piece of anatomy is the blood vessels. The superior mesenteric artery and vein, they go over the duodenum. Always look for that. Superior mesenteric A and B go over duodenum. So there you see it there, and if you just see them going over duodenum, you can identify them. Okay? Here they are there. Okay, that's their SMA, superior mesenteric artery. There it is there. This is a backwards view. That's it right there. Superior mesenteric artery and vein. Actually, don't let that one sneak up on you. That's inferior mesenteric vein. Yeah, that's on your study guide too. Okay. All right, here's, well, do you see it here? Superior mesenteric artery and vein. There's the rugae, there's the plica, there's the chyme that's spiraling through. Okay, let's talk about the blood supply to this region. Coming off abdominal aorta, there's three main branches that come off. They're all singular, they're not paired. The first one that comes off at around the level of T12 is the celiac trunk. Right there, I'm pointing to it. Well, the next one will be, I'll say SMA, superior mesenteric artery. That one down there. Inferior mesenteric artery. Now the celiac trunk has a lot of branches to this stomach duodenum region. So let's kind of use this picture to map them out. So abdominal aorta, and you have first branch coming off, the celiac trunk, called number 1. The first branch it gives off, it goes up and to the left, and it's going to go going to follow the lesser curvature of the stomach. It's called the left gastric artery. So first branch comes up, goes off to the left. 2. Left gastric artery. There's another branch going off to the left. It goes all the way to the spleen. This one here. Splenic artery. Splenic artery. All right, let's follow the major branch that goes off to the right. It's the common hepatic artery, number 4. It's common to a couple of things. Now, the first branch it gives off, it's hard to see. The first branch it gives off goes down to the stomach duodenum. It's right there. It's called the gastroduodenal artery. Gastroduodenal artery. The next branch it gives off follows the curvature of the stomach again. It's the right gastric, it's right there. It's going to form an anastomosis with left gastric. Right gastric artery. Now, it'll continue on as the proper hepatic artery is going to go to liver. Anyways, the name of that structure is proper hepatic artery. I put proper in parentheses. Sometimes books don't call it proper hepatic artery, they just call it hepatic artery. Either is fine. I think your book does call it proper hepatic artery. Now there's a couple of more. There's one branch on the right side. It's going to follow the greater curvature of the stomach. It's coming off of the gastroduodenal 8. It's the right gastroomental artery. Right gastroomental artery. And it's going to anastomose with the one on the left. I'm going to put a little branch in there. The last one, number 9. It's the left gastroomental, number 9. Left gastroomental artery. So those are all the branches that supply blood to this region. I have some other pictures here that you could study. Some of the branches are missing, but you have to know them all. This picture shows the stomach cut away so you can see that.
Can you please show us on the other image, number 7, 8, and 9?
Oh, okay.
Sorry.
All right, so here's gastroduodenum. But you can see behind the stomach, there's a branch coming off of it, right there. So that becomes gastroomental on the right side when it follows the greater curvature of the stomach. Here's splenic. See that branch coming off right there? What is this?
The left.
Left gastromental. Let's back it up right. What if I point right to the root? What are you gonna call it? Celiac trunk. What is this one? Left gastric artery. What's this one? Splenic. What about right here? Common hepatic. Now look at that first branch that goes down. What's the first branch going down? Gastroduodenal. But if it follows the greater curvature of the stomach, it's the gastromental. On the right side. What's the second branch coming off right there? Right gastric. What about there? Hepatic artery or proper hepatic artery. And they're shown here too. For example, there's a nicer picture of the gastroduodenal. Okay. What's that one that's cut? That's right gastric, but it's been cut, but it's still there. Look at this one. This goes up into the left. That's left gastric, so that's splenic. So it's a little different. Here are those two shown side by side. And here it's kind of shown just kind of close up. I just kind of zoomed in on this one to help you study. So just kind of just repeat. Just keep going. Left gastric, splenic, common hepatic, gastroduodenal, right gastric, proper hepatic artery. Just keep rehearsing so you got the blood supply down. I want to move on to the liver and pancreas. We'll do pancreas first. In terms of anatomy, it's not very much to look at. It's just a gland. But it does have both endocrine and exocrine gland function. And so for the exocrine secretions, it uses that pancreatic duct that we talked about. I call it the main pancreatic duct. It's like an inverted tobacco pipe. Here it is there. There's a duodenum, but this is the main pancreatic duct of the pancreas. There's some facts about what it secretes. I'm going to erase this. For digestion, it's primarily exocrine function, but I'll mention both. I'm going to focus mostly on exocrine function, okay? Because the juice it secretes, it can be pancreatic enzyme-rich juice, or it can be pancreatic bicarb-rich juice. That's basically what I focus on. That's what I have listed there. Pancreatic-rich juice is either going to be enzymes or bicarb, and that's the main function of it. And it's mostly water. The bicarb will neutralize the acid, but those enzymes are listed here. The enzymes digest, well, as I list there, proteases will digest proteins. The amylases will digest carbs. The lipases will digest fat. And the nucleases will digest nucleic acids. Now that's everything. And as an example of how they operate, I'll use proteases to show you how the pancreatic enzymes are activated. So again, the concept is you want to secrete the enzymes in an inactive form. You don't want to activate them until they reach the lumen of the small intestine. Release This prevents autodigestion. That's what I say on the slide. Prevents autodigestion. So as an example, trypsinogen is a protease, but that's the inactive form. However, when it gets to the lumen of the small intestine, there's a membrane-bound enteropeptidase. Membrane-bound because it doesn't escape and prematurely activate these things somewhere else. It's membrane-bound in the lumen there. And, well, it's an enteropeptidase. What it will do is it'll activate trypsinogen into trypsin. Trypsin is the active form. It's the protease. And this particular trypsin will activate other proteases. Kind of a chain reaction there. Activate other proteases. Again, so that you don't auto-digest, you just activate it inside the lumen. It's very ingenious. That's how it works for all of these pancreatic enzymes. Now, I do want you to know the histology of the pancreas, and it's called the acinar or acinus structure, which means shaped like a mushroom. Okay, that's kind of what you see here. Oops. So this is emphasizing the exocrine function. Let's look at that bottom structure there. That's useful to look at. Those cells in the pancreas that are the duct cells colored blue, you want to differentiate those from the acinar cells, which are colored orangish. They're the bulbous-looking mushroom-shaped cells. Well, anyways, those duct cells, well, let's back it up. Okay, if there's acidic chyme that reaches the duodenum, that's a trigger for the release of secretin to target the pancreas. Specifically, secretin targets only the duct cells. And in response, the duct cells will release the bicarb-rich juice. That will be secreted into the pancreatic duct there. If there's, say, fat in the food you ate, fat will trigger the release of cholecystokinin, CCK. CCK will target the acinar cells to release all the enzymes from the pancreas that we just got through talking about. So differentiate bicarb from enzymes. But they're all mixed together in the pancreatic juice. And the pancreas will release something like 1 liter to 1.5 liters daily. Well, the other thing I mentioned on the next slide is to remember what these things do. That fat digestion is helped by CCK because there's lipases in there to help digest the fat. And the acid is neutralized by the bicarb-rich juice. So that's really the point of those juices, for fat digestion and acid neutralization. A third thing to remember is the endocrine function. Not only do you have the bicarb-rich juice and the enzymatic rich juice, you have GIP. GIP is released in response to glucose in the food chain. GIP. Let's remember that there will be external to the acinar structure little pancreatic islets with beta cells, right? There's little clusters of cells. I don't know if you remember looking those up on the microscope slide. The little pancreatic islets. Anyways, GIP will target those cells. And in response, insulin will be released to the bloodstream. Not to the main pancreatic duct. That's endocrine function. But I do want to mention it because it's important for digestion. So focus more on the pancreatic physiology there. So yeah, the other major organ of digestion that's an accessory organ is the liver. The liver is the biggest solid organ in the body, so there's a little bit more anatomy there. It's about 2% of your body weight. It has a reddish-brown color. It's receiving a lot of blood. It's receiving all the blood returning to it from the GI tract through the portal vein. So it's nutrient laden. It's laden with the products of digestion. It's got all the food you ate. Anything you stick in your mouth, it ends up in the liver because of the portal circulation. That's important to remember. The liver has to process it before it can enter the general systemic circulation. Think of it as a storehouse for glycogen, and also I'll focus on its production of bile. Bile is an important agent for digestion, especially fats. Between meals, it's stored in the gallbladder. So if you look at the liver just by itself out of the body cavity, it looks like this picture here. There it is in the body cavity. You have lobes of the liver. There's 4 lobes, but you can only see 2 really here. So it looks like you got something like that. They're covered with a peritoneum top here. There's a little bit of green, little green pouch there. That's the gallbladder. Well, anyways, let's focus on the lobes for now. The big lobe is the right lobe. And then this is the left lobe. So you have right and left lobes. We'll see the other 2 lobes when we look underneath. So here's that picture isolated. And you can see the 2 ligaments, falciform and round ligament. This right here, that's falciform. It attaches to the front body wall, to the anterior ab wall, holding the liver in place. Attaches to anterior ab wall. This ligament down here that's round is the round ligament. It's also called ligamentum teres because teres means round, but I want to stick with round ligament. That's easier for you to remember. The ligamentum teres, that's the same thing. Remember that, so you don't ask me later, what's ligamentum teres? It's the round ligament, and it contains an obliterated umbilical vein. Okay, that's where it is when you're an adult. It's obliterated because you're not using it, but you certainly were using the umbilical vein during fetal circulation. But it's kind of It's in there. It's hard to see. Okay. And it's that round ligament at the bottom. Contains umbilical vein. Well, here's a picture of the anterior abdominal wall. So it's the inside of your front body wall. That's what you're looking at there. And I'm pointing out the round ligament in both locations. So there's the round ligament there. But here's falciform. And then round ligament at the bottom. And it contains the umbilical vein in there. Right? And the umbilical vein goes all the way down there. And it's met by two umbilical arteries that come up to meet it. There's one. Remember, these are branches of the internal iliac. There's two. So you have two umbilical arteries. And they exit through the belly button. So that's the inside of your belly button. Okay. And they all exit out through there. That'll be the umbilical cord on the other side. When you're an infant, or not when you're an infant, when you're in utero, inside mommy. Well, anyways, you should know those structures. Round ligament, you should still know. Two umbilical arteries, one umbilical vein going through the belly button there. Okay. So if I point to at the very bottom, I'm going for round ligament. But what do you think I'm going for if I point to here and have you identify it? Falciform. It's falciform all the way down to there. And remember, in the liver, we have a little bald spot. We call that the bear area. I like it when the names make sense. Why is it called the bear area? Because it's bare. There's no peritoneum there. Okay. Here's the, well, it's actually this, our model, the underneath view of the liver. Okay. Basically what you got there. You have inferior vena cava. IVC. And then you have a blood vessel going into it, the hepatic vein. You have some, I'm going to draw this there. That's the round ligament. You have this big opening there. It's called the doorway to the liver, the porta hepatis. Porta hepatis. The doorway to the liver. Things go in and out of there. Just to reorient you, this is the left lobe up here. This is the right lobe over here. You can see your other two lobes, the caudate, the quadrate. The quadrate just means four sides. It's right here. quadrate lobe. The little tail-like lobe up here is the caudate. And you have a little gallbladder by the right lobe, by the quadrate lobe. There's gallbladder. Now the gallbladder is going to send a duct out right here. It's going to send out the doorway. So it's going to go out there. Okay, anyways, this little duct is called the bile duct, and bile is coming out of the liver from this point. So, you got porta hepatis, one thing coming out, bile duct. Two things going in are two blood vessels, proper hepatic artery and portal vein. Proper hepatic artery, I'll use red for that. And then I'll use blue for portal vein. So both of those are taking blood in. The portal vein is all the nutrient-laden blood that came right from your intestines, but it does not have oxygen. Gas exchange already occurred at the intestinal capillaries. So that's why you need another vein, another blood vessel, hepatic artery, to supply oxygen-rich blood. So these are the contents, these three things are the contents of what's called the porta hepatis. Okay? So students always they confuse, sometimes the hepatic vein is confused with the portal vein because sometimes they call it hepatic portal vein. But understand they have completely different functions. One is taking blood into the liver, portal vein. One is draining the liver, hepatic vein. So blood's on the way out up here. Blood's on the way in down there. Okay, so know what's going on here. Blood's coming in, blood's going out. You should know that.
Can you show us where the porta hepatis is on the picture on the slide?
Yeah,
It's that
right here.
hole over there.
This whole area. Look for three things. Boom, boom, and boom. What's the blue one? Portal vein. And they're labeled proper hepatic artery, bile duct. Yeah.
So it's not just the one side that you have drawn on the board, it's the whole thing around.
Yeah, it's referring to this opening.
Okay.
They call it a doorway because things are allowed to enter and exit. Porta hepatis. There's the two views side by side. And I think it helps to kind of look at the whole biliary system. The gallbladder, I kind of just drew it there, but just to kind of look at more pictures of the gallbladder, it's not much to look at. It's just a green sac. It lies along the right edge of the quadrate lobe. It is bluish green. It can hold about 30 to 60 ml of bile. Here's another picture of it. I showed this one to you before. It's stimulated by CCK. There's the other end. You squeeze it there, you relax that end, and bile can spill into the duodenum there. This is probably one of the better pictures of it in your atlas.
Professor, if you take out your gallbladder, is there like a bypass that it goes into?
No, I think it just goes. Oh yeah, actually, let me talk about that. So your liver produces something like 100 ml bile daily. Now this bile that the liver produces is called, is considered dilute bile. We call it dilute. Now some of this bile is diverted to the gallbladder if you still have one. About 450 ml bile daily. They say that this is produced, 450 of the 900 is produced between meals when you're not eating. But between meals, there's no CCK, so what happens is that sphincter is tight, so it backwashes into the gallbladder. Now, if you don't have one, I'm not sure what they might do. Okay. So yeah, I guess I don't know.
So I don't have one, but I don't know.
Did the doctor tell you?
I don't remember asking.
Okay. Well,
Well, it just, there's no storage, so it just goes when you eat, it just.
yeah. Yeah, so basically, if you don't have a gallbladder, you still have bile. You just have the dilute kind. But the one that's produced between meals, that's normally diverted. If you have a gallbladder, this will be diverted to gallbladder. Or it's stored and concentrated. If you looked at the inside of the gallbladders we see here, the surface is kind of pocketed and not smooth, and that helps to concentrate the bile and the bile salts. Bile is concentrated. So if you have a gallbladder, about 500 mils of bile, it reaches the intestine, like right there, daily. 500 ml of bile reaches the intestine daily. And so it would be a mix of dilute concentrated, dilute and concentrated bile. But if you don't have a gallbladder, it's just mostly dilute. And usually you're instructed to change your diet. Like, they tell you to eat less fat. And when you do eat fat, maybe I imagine one might notice more loose stool. Because, the bile, it helps emulsify the fats. But you still got the bile. The liver produces the bile. The gallbladder just stores it. And actually, when I open cadavers, I wonder if I'll see the gallbladder. It's usually not there. The removal of the gallbladder is one of the most common medical procedures. One time we had 2 cadavers, and I was 0 for 2. 0 for 2, no gallbladder. We just don't know until you open it up. The other thing is, so the between meal thing, there's no CCK, this is tight. So you produce the bile, it backwashes into here. Notice that there's no sphincter to this gallbladder. It has a spiral groove instead. And that spiral groove, it helps keep the bile in here. Okay? It doesn't go out easily because of that spiral groove. But you should know all of these little ducts and how they're connected. Those are things in your study guide. So right at the top, you see these 2 here. You have right and left hepatic duct. Right hepatic duct. This one here. Left hepatic duct. They merge to form common hepatic duct. Now the gallbladder has a cystic duct that it sends. meet up with the common hepatic duct. So that's cystic duct. And then the cystic duct and common hepatic duct, they merge to form the bile duct that goes to the intestine. So that's the anatomy. We call that the biliary system. And it helps to practice with some of these pictures that I've included here. If you look at a model of the liver, if you see the gallbladder, just orient yourself, because you always know the gallbladder is on the right side. That's the right lobe, right side. Therefore, that's the right hepatic duct. Therefore, that's the left hepatic duct. Common hepatic duct, cystic duct, bile duct. And just keep practicing. There's portal vein, hepatic artery. On this one, oh, I flipped it upside down. It doesn't matter. If that's the gallbladder, that's the right side. Therefore, that's the right hepatic duct, left hepatic duct, common hepatic duct, cystic duct, bile duct. There's portal vein, hepatic artery. They're always going to show you that. Can't see it there. Okay, here's our liver model. Right there. Okay. Let's orient ourselves. There's the gallbladder. So I know that's the right hepatic duct, left hepatic duct, common hepatic duct, cystic duct, bile duct. They color the portal vein purple, hepatic artery. Don't confuse portal vein with hepatic vein up there. We'll pick it up at the liver lobule next time. When you come back from break, we'll just have time to study the model. Let's come back at 1 o'clock.